Okay, so today we're going to do Shor's factoring algorithm after 15 lectures of preparation. Great, so let's recall what we had finished working out last time, which is actually all the quantum stuff we're going to need for this algorithm. In fact, today's lecture is going to be 100% classical algorithms, classical number theory. There's going to be 0 quantum in it. So we're almost done. Okay, so let's say that you have access to a quantum circuit, QF, that implements some function f, mapping the integers from 0 through n minus 1, capital N minus 1, into some set that I had been calling colors, although it's just some sets, of strings. And in fact, we're going to, remember today that it's a set of n-bit strings. Okay, and capital N, you should think of it as 2 to the little n, where little n is the number of qubits that go into this quantum circuit. So that should be like a modest number, whereas capital N is an enormous number. And we're assuming that the function f is L periodic, or essentially L periodic, in the sense that for any integer x, f has the same value at x and x plus L and x plus 2L and x plus 3L and so forth. But today we're not going to really think of this as the integers mod n. Just think of it as integers. And so this is not mod n. So there's no wraparound. So L does not, in order for this to happen, L does not need to literally divide capital N. So if you get really close to n here, you don't wrap around to the beginning. Okay, that's fine. And also, not only are these values equal, they're like no other equalities. So I mean, on each of the groups of the form x, x plus L, x plus 2L, etc., f has the same value, and on different groups it has different values. Okay, and so as we saw last time, by the combination of Simon's algorithm together with the quantum Fourier transform for the integers mod n, we saw that with a modest size quantum circuit, using about n squared gates, this is for the Fourier transform. In fact, you can get it down to about n log n. Plus however many gates you need to implement the quantum circuit for f, which is, if you're deriving it from a classical circuit that you've just made reversible, is about the same number of gates you need to compute f classically. You can get some kind of clue to L. Okay, so we kind of left it as this. We didn't exactly see how to find L. But we got something that looked like a pretty good clue. Remember, in the situation where capital L divided evenly into capital N, you just got a random multiple of capital N over capital L. And from that, it was easy to derive capital L, but it was an annoying situation because if capital N is the power of 2, then only powers of 2 divide capital N evenly. But in our setup where capital L does not divide into capital N, what do you get? You basically get a random multiple of capital N over L, but rounded to the nearest integer. See, now capital N over L is not an integer anymore. And at the very end of the last lecture, what I showed is basically something like this. It's like you get, actually for each integer k between 0 and L, there's at least a 0.4 over capital L chance. So at least a 40% of uniform chance that you'll get out of your quantum measurement the nearest integer to k times capital N over capital L. And for the purposes of this, you can just assume that when you don't get that, you just get some junk, or you'll give up. But it's not a big deal because you can just try again, and you have a 40% chance of something good happening. And in fact, it's really not junk. When you don't get this, the next most likely thing that happens with another constant probability is you'll get one of the second closest integers to k times capital N over L. That will also be good enough for us, but let's just for simplicity say this is our good event, and we'll just bank on it happening.
So we can't pick k?
No, k is random. So when you when you do the quantum Fourier transform, you basically get a spiky looking function, which is essentially uniform with spikes at distance capital N over L. So they're kind of concentrated near the multiples of capital N over L. And then you measure. So you get a random multiple of capital N over L. So you have no control over what k is. Yeah?
So I presume in the following algorithm, we're going to throw out the 60% useless ones and just use the 40%.
Yeah.
How do we distinguish?
Good question. How do we distinguish? Yeah, you want to know whether you have the right answer. Well, there's a couple of ways. One is if you have a candidate capital L, it's pretty easy to check whether it's good, because you can just query. Once you have this promise, you can you pick your favorite x, 0, and check f of 0 and f of L and see if they're the same. And that way confirm that you have L.
It's also valid for 2L, so kind of.
Right, that's a good point. So it could be that would also be valid for if you accidentally got 2L. Okay, that's a good start. The other factor is this is all ultimately going to be in service of a factoring algorithm. And so factoring is checkable, right? If you have a number and you like think maybe you factored it correctly, and you can check whether you factored it correctly by multiplying your supposed factors together. Actually, it's not quite as easy as that, but you'll see as we go along that it won't worry you too much if you get like a wrong answer here. It's a good point, though. OK, good. So what in fact are we going to do today? There's two parts. And part one, which is really due to Shor. I mean, this was also due to Shor, but this part is also due to him. It's how to use this clue to actually find L. You only really need one, but OK, so we actually saw how to do that in the case where capital L divides capital N. We also saw how to do that in Simon's algorithm by solving systems of equations. And Shor will also show that you can, from this clue, like actually find capital L, which is good. And this will be a totally classical algorithm. I mean, there's no quantum here. It's like a fun problem, actually. If you get this, how can you figure out what capital L is? So this part is efficient and classical. And then, well, the second thing we need to do is, how does this help us factor numbers? And the answer to this question was like already known in the mid-70s. More particularly, as we'll see, they knew that if you could figure out the order of elements in like a multiplicative group of integers, which is basically like finding the period of like a big periodic function, then you could factor numbers efficiently. So this is also classical and just involves some number theory, and we'll talk about it today too. OK, and we'll actually take them in the reverse order. First, I'll do part 2, and then I'll do part 1. But just before getting there, let me say, what do you get if you put this all together? If you use simple algorithms, if you use simple algorithms, then this will give you about an m cubed gate circuit, quantum circuit, for factoring m-bit numbers. And if you instead use a more sophisticated algorithm, which basically means remembering that you can multiply two m-bit numbers in basically around m time, maybe m log m, log m time, you can get this down to more sophisticatedly something like m squared times log m, maybe times some log m or something. OK. So it's, and then you should think of m as like 1,000, maybe. OK, remember at the lecture 1 or 2, we talked about the RSA challenge, this cryptographic challenge, where there's these well-known numbers, and you get $100,000 if you factor this 1,024-bit number. OK, and nobody's done it. The record for factoring these numbers is in the 700 bits, and for 2,000 bits, it seems totally hopeless. But if you use this right, then this is a quantum circuit with merely a million or so gates, a few dozen million gates. OK, or you could think of m as, 100. It's still quite interesting. OK, so this is very efficient. And you should compare this to, classical algorithms. The naive algorithm, which is, given a number to factor, just try dividing it by 2, 3, 5, 7, 9, 11, et cetera. Well, you need to go up to square root of the maximum possible number, which is 2 to the m. So this is 1.4 to the m. OK, and this is exponential, right? So this 1.4 to 1,000 is some unphysically large number. And even the most sophisticated ones are, exponential in m to the 1/3. I don't know, so some constant like 10 to the power of the 3rd root of m. It's still exponential in m. OK, so I mean, this is the greatest, the ultimate application of quantum computing that we know about, an efficient algorithm for factoring integers, and we only know an exponential one classically. It's a shame, actually, that we can't get it down to quasi-linear. It'd be cool if this was a nearly linear time quantum algorithm. Whether or not you can do that is an interesting question. I'll actually point out where the bottleneck, the efficiency bottleneck, if you want to get that m squared even lower, is, and it comes in a completely classical part of the algorithm. So it's an interesting open question if you can improve that. OK, so I'm going to start with 2. How can being able to find the period of a periodic function help you factor? OK, so let's assume that we've done part 1. And so we just have the ability, like once you have such a quantum circuit F, boom, you can find its period for an L periodic function. OK, so how do you use that to factor numbers? Well, there's a little number theory involved. It's actually moderately similar to the Miller-Rabin primality test, if you've ever seen that. OK, so this is like a reduction. It's called a reduction from factoring. Reduces to what's called order finding. And I think that maybe this was known folklorically in the 70s. I think it first appeared in print in like a 1976 paper of Professor Gary Miller about primality testing. And there's a nice write-up of all these kind of number theoretic reductions by Heather Wall in her master's thesis from the 80s. So you can also see it there too. OK, so what is the factoring problem? Like the input is like a big number. Let's say B, a big number. And we'll call it little m bits, because I want to reserve little n for that thing such that capital N is 2 to the little n, and it won't be quite little m. But think of m as like 1,000 or something. OK, and your goal is to get, of course, the prime factors of B, the prime factorization of B. And for simplicity today, I'm going to make the problem a bit easier. You don't need to do this. Shor's algorithm works in all cases. But I'm going to assume that B is the product of just 2 primes. And let me just try to assure you that this is not a big deal. Why is this not such a big deal? First of all, you should think of them as like, maybe each being m over 2 bits, so like the product of 2 500-bit primes. First of all, this is the main case of interest for cryptography. So in this RSA crypto system, the secret key is always taken to be the product of 2 large primes. So that's the main application of factoring, breaking these things. Also, it's intuitively the hardest case, right? I mean, if B is a number, like with plenty of prime factors, then it should be easier to find them, right? Particularly, they should also be smaller, I mean, because they have to multiply together to give an m-bit number. So I mean, this seems like the hardest case when there's just 2 factors you're trying to find. Of course, I should mention, by the way, like if it's just a 1 prime, you can do it efficiently in polynomial time. You can test primality. And finally, this is just to make the lecture go a little bit more smoothly. You don't have to do anything fundamentally more challenging in the general case. There's just a bit more bookkeeping that I would have to tell you. OK, so it's basically, you're not losing anything to restrict to this situation. OK, so how are we going to do it? OK, so as I said, it's a little bit like the Miller-Rabin primality test, if you've ever seen that. Otherwise, it's some elementary number theory thing. OK, so I'll just tell you the main trick and goal for this to factor B is to find non-trivial square root of 1 mod B. OK, so for all what we're going to talk about in this part 2 discussion, we're going to be mainly thinking about like the integers mod B. Because B is your input, this big number. And well, first of all, what is a square root of 1? Well, it's just like it sounds like. It's r such that r squared equals 1 mod B. And what does non-trivial mean? Well, this just means that r is not 1 or minus 1. Those are obvious square roots. Mod any number. So we want to find some other square root. Okay? And by the way, if b is like a prime, then this is a little number theory that you probably know, then the integers mod b are a field, and then therefore this is also the same as the equation r squared minus 1 is 0. This is a quadratic equation, and quadratic equations only have two roots over a field, which are these. So if b is a prime, then there are only two square roots of 1, plus or minus 1. But when b is, let's say, the product of two primes, it turns out there's 4. And so we want to find one of the other two. Okay, okay, so that's going to be challenging, but like, what the heck does it have to do with factoring? Well, it turns out if you can somehow manage to find this r, you're totally done. You're home free. It's basically over. So why is that? Well, let me just write r squared minus 1 as r minus 1 times r plus 1. Okay. And remember, b is, in our assumption, p times q. So, I mean, let's take a look. What does this mean? This means that this number is a multiple of pq. So it's some multiple of pq, so pq divides whatever it is. So pq divides this thing. And what would be cool is if like p divided one of them and q divided the other. And actually, that has to happen. It can't be that like, these are primes, so they got to divide into one of these two things. I mean, collectively, p and q have to appear in the prime factorization of this product. And it's not like p and q can both divide r minus 1, because we don't have this. Because that's literally saying that r is congruent to 1 mod pq, which is b. And we're saying r is not 1. And it can't also similarly be that pq divides r plus 1, because that would be saying that r is minus 1 mod pq, which we're prohibiting. So p and q as primes have to divide this product, but it's not like both of them can divide one of them and not the other. So you conclude that, either p divides r minus 1 and q divides r plus 1, or vice versa. And then you're in great shape, I mean, because you know p, so you know r. So just take r plus 1 and compute, or r minus 1, it doesn't matter. Let's just say we do r plus 1. Compute the GCD of it with b, which you also know, that's your input. And it's going to be p. Or, well, I guess q in this case. It's going to be q or p, whichever one divides r plus 1. And that's it. You've got q, and then you can divide it into b and get p, or vice versa. Okay, and as we saw on the homework, I mean, this was maybe on the first or second homework, you can do this efficiently, classically. The naive algorithms take about m squared steps for m-bit numbers. There's even like ones that take close to m steps. Okay?
Is that less equality?
Pardon me?
Why is that less equality?
Which one? This one?
Yeah.
Oh, well, it's the greatest common divisor of r plus 1 and b, so it's a divisor of b. And b only has like p and q as divisors. Great, so that's like the smallest trick. And so, great, so I mean, factoring, we just need to find this non-trivial square root of 1. Okay, so that's the main part of this. So how are we going to do that? This is where the period finding comes in. Okay, now it gets into like a little bit of number theory. So recall from your homework, maybe homework 3, number 5, and homework 4, number 6. We looked at this object, which is the set of integers mod b, but like viewed sort of multiplicatively with multiplying as the main operation. So this is all the integers, mod b, with that are coprime that make a GCD of 1 with b. So actually, in our case, where b is p times q, it's very simple. It's all the integers mod b except for the multiples of p and the multiples of q. So it's almost all the numbers mod b, just not the multiples of p and q. And as we saw in the homework, this is also the same as like the integers mod b, such that you know, a reciprocal exists. You know, where there is a number which, when you multiply it against a, you get 1 mod b. Okay. And that doesn't hold if, you know, let's say if you're a multiple of p, then like anything times u is a multiple of p, and so it could not be congruent to 1 mod pq. But okay, this is what we're going to be studying. Okay, and so now I'm going to tell you the algorithm for finding r. It's actually a randomized algorithm. But it works with pretty high probability. So I'm going to describe a randomized algorithm that finds an r with pretty high probability. And then, you know, this gets at one of the original questions, like if you find this r successfully with pretty high probability, whatever it is, you can just do this. You can take the GCD of r plus 1 with b, and you know, whatever it is, like hope that it's one of the prime factors of b, and then you can test that yourself. Okay, and if it doesn't, you just say, well, I guess maybe I didn't find a good r. And then you just try everything again. Okay, so our algorithm starts out kind of classically. This is the algorithm for finding r. So first, pick an integer a in this set zb star uniformly at random. Now, one question is like, how exactly do you do this? Because what is zb star? It's like everything that makes a GCD of 1 with b. It's like everything except the multiples of p and q. But you, the algorithm, don't know p and q. So I mean, how do you like not pick them when you're doing this step?
If you pick one of the multiples, you're done already.
Exactly. So what you just do is don't worry about it first. Just pick a uniformly from all the possibilities at random. And then if you're worried that it might actually not be in ZB star, that it might be have GCD, a non-trivial GCD with B, then just compute the GCD, A and B. And if it's not 1, well, it's P or Q, so great, you're done. Yeah.
So how are we picking uniformly at random except by just numbers 0 to b?
Yeah, that's what we do.
Okay.
So I mean, if you're worried about like, oh, if you only have access, usually, you know, if you have like, I let you as like a primitive operation in classical computing, like pick a random number between 1 and 7, let's say, or if you don't like that, you can pick like a random string of m bits, and then just reject it if it's 0 or if it's bigger than b minus 1. And it'll take you a few tries on average before you find a number in this range. Okay, but okay, this actually happening, this happens with like, you know, absurdly low, exponentially small probability. So it's not like this is ever actually going to save you, but anyway, it's fine. I mean, a miracle could happen and you could be done right away, but otherwise, you've accomplished this. Okay. So now we really get into the number theory. So basically, for those who are familiar with it, and I guess it was on the homework, so you should be, but I'll repeat it. We're going to be interested in the order of this random A in this multiplicative group of numbers mod B. Okay, so this is not an algorithmic step. This is like a mathematical analysis step. So let me say, like, hypothetically, let us, you and I, consider the following. Well, these numbers, A mod B, and A squared mod B, and A cubed mod B, and so forth for a really long time. And it's a fact that you'll actually eventually hit 1 when you do this. So, and let's go to the first point at which you hit 1. A to the something equals 1 mod b. And this something is called the order of A. And let's just call it L. It's called the order of A. And it's the first, it's the least j such that a to the j is 1 mod b. OK? And let's see. First of all, I also want to say that all these numbers up until this point are distinct. So for j and I less than L, say, because if they were the same, like if you had aj equal to ai, you can use the fact that a reciprocal exists and multiply by it on both sides like I times. And you get that like a to the j minus I equals 1. This is all mod b. And so there'd be like an earlier time when you'd hit 1. OK? So this also implies that you'll eventually hit 1 because it's a finite set. So if you keep doing this, you'll eventually do a repeat at some point. And then by this argument, you have a 1 somewhere in the list. OK, so this is also some elementary number theory that shows that you'll eventually hit 1 at some power, which we'll call L. And prior to that, all these will be distinct. And furthermore, after that, it will repeat again, right? Because a to the L plus 1 is this thing times a. So it's a to the L plus 2 is a squared, mod b, etc. So great. This is looking familiar, right? This actually shows that this function, f, mapping, actually the integers, if you will, but let's just say like numbers, into, well, the elements mod b is, L periodic. Maybe you should like think of it as like f sub a, because it depends on what random a you chose. And L also depends on a. OK, but for some L, it's L periodic. OK, and I'm going to consider the domain of this function just to go up to some big integer, capital N minus 1. And I'm intentionally letting it go up to past like even b. So I'm eventually going to take, in the algorithm, this capital N to be much bigger than b. But anyway, this is true. So I mean, fa is this function. Oh, I didn't write it. Sorry. This is very confusing. Defined by fa of x is a to the x mod b. It's very important. It's L periodic.
Why do you want N to be bigger than B?
For a much, much later part of the argument. Basically, for the part of the argument where I use these clues that I get out of the quantum algorithm, these clues for L to find L. But it could be whatever I wanted here, actually. I mean, it's periodic indefinitely over the integers. So not only is it periodic, but I mean, this is a crucial point. This is a function that it's easy to compute classically. This was also on the homework. This is the modular exponentiation problem. And it's classically efficient to compute. OK, this is the thing where, x could have like, thousands of digits, but you like, you compute a squared and a to the 4th and a to the 8th and a to the 16th, and by repeated squaring, and you combine them appropriately to get a to the x, and you're always doing it mod b so that like the answer size stays small. So hopefully you remember all that. And again, if n is 2 to the little n, and b is m bits, so the integers mod b our subset of 0, 1 to the m. And this is the thing that's like colors, if you will. Yeah, you can compute this in computable classically in time something like n cubed if you're not too sophisticated. And if you are sophisticated, maybe like something like n squared log n log n. If you use some sophisticated fast multiplication algorithm. Okay, as we discussed earlier in the class, much earlier, if you have an efficient, time-efficient algorithm, you can convert it to a classical circuit with about that many gates. So if you're not sophisticated, let's say m cubed gates, classical gates, and then you can, use this trick of, doing reversible computation to convert it to a quantum circuit with about the same number of gates. And this is our Q sub f sub a, with about the same number of quantum gates. Okay, and now we're like perfectly in this scenario that we talked about last time, where we have a quantum circuit that computes an L periodic function, and like our goal in life, or our ability, will be to find L. Yep.
So we're picking n that is how much bigger than m?
It's going to turn out to be like not that much bigger, like maybe 10m.
Is it because you don't want your clues to be small? It's good if your clue is small, right?
It's going to be because
Like imagine you can like actually do from 0 to like L minus 1, then like you're in a great shape, right? So kind of like the smaller your range is, the better.
well, your clue is like a random multiple of capital N over L.
Yeah.
Right? So if capital N is like
L, then you're in a great shape.
no, why?
Capital N is like,
Is L, then it's really good, right?
Well, I mean, if L is like somewhere in the range of I don't know, n over 10. I mean, you'll see at the end, I guess. If you were getting exact, like if L happened to divide n and you're getting exact multiples of n over L, then you wouldn't care how n and L related. But because of this issue that you're only getting these clues and you have to like kind of fudge around a little bit, it's going to come in there. Okay. Good. So you're going to apply the quantum algorithm to this, and you're going to find L. Or at least you're going to have a decent chance of finding capital L. And finally, now we'll talk about how figuring out L helps you figure out a non-trivial square root of 1 mod b, which lets you factor. By the way, this is the part that's the efficiency bottleneck for Shor's algorithm, computing modular exponentiation. So we don't know how to do this operation in near linear time. We only know quadratic time algorithm for it.
There is like any lower bounds of like the efficiency of how you can do exponentiation?
No, we're not good at proving like lower bounds. Although it's kind of a hot topic these days, trying to prove like certain algorithms like require quadratic time. Well, it's a good research question. We don't know any lower bounds like that suggest that you can't do it. Another famous question that's related is we know efficient algorithms for computing the GCD of two integers, and it's an open question of whether they're like highly efficient parallel algorithms or not. That's like a great problem in the algorithmic complexity of number theory. Okay, so this is like the most technical piece of the number theory coming up. Remember, still our goal is to find this non-trivial square root of 1 mod b. And through the magic of quantum, we've figured out, say with reasonable probability, L, the order of this randomly chosen A. So here's the idea to get this r, which is like this non-trivial square root of 1. Okay, we know A, we chose it at random. We know B, that's the input. And now we just got capital L, that number, such that A to the L equals 1. So how about just do r is A to the L over 2? Then r squared would be 1. This is all mod B. So let's question mark, happy face. Well, there's two issues with this. One, well, L better be even or else this doesn't make sense. So we need some luck here. L should be even. Otherwise, this is not an integer, so it doesn't make sense. And what's the other piece of luck that we need? Yeah.
R is not -1?
Yeah, exactly. Or 1. So we need that. Oh, well, I guess r would not be 1 because L is the least power of A that gives 1. But we need like r is not -1 because we have to get like a non-trivial square root of 1. And I say luck because it comes from the chance of choosing A at random, whether or not these two things happen. So if both these two things happen, then this makes sense and it works and we're done. So the final bit is a lemma that says the probability over the choice of A that both luck 1 and 2 happen is good. In fact, it's at least a half. It's quite large. So you pick this A at random, you do your quantum, you get back L, and then there's a half chance that not only is it even, but and that allows you to form a square root of 1 in this way. There's a chance that it's like a non-trivial one, that it's not 1 or -1. Okay, and then you're in good shape. You take the GCD of r plus 1, let's say, with B, and you find either P or Q. And if any of these lucky things goes wrong, it just means that like finally when you keep trying the things that you think might be correct, at the end, they don't work out, and you don't get that GCD being P or Q, a factor of B, but you just try everything again, and when you finally factored B.
Isn't it just like the luck 1 is already 1/2?
Yeah, it's not too hard to show. This happens with probably at least a half.
Yeah, but then you need and the second one.
Yeah, but
And it's still like half. Like I would expect a quarter or something. Like.
Well, first of all, it doesn't. You're right in that it doesn't matter too much, but no, it's actually a bit more like if you think about these things in a somewhat naive way. Like this one actually happens kind of with probably like 3/4 for a reason. But this is the last number theory lemma, and it's like moderately tedious. So I'm not going to prove it. It's going to be on your homework. And like it'll be the final grand culmination of like all those like annoying number theory exercises I made you do. You need to know the Chinese remainder theorem, which is one of your problems. And you need to know that this is like a cyclic group, which has a generator. And then you have to do like a little bit of case analysis. Okay, so I could actually do the whole thing in like 10 minutes, but I'm not gonna. So this is, this at least feels like it has like a reasonable chance of happening with constant probability. And also, I told you there's like 4 square roots. It's not hard to show with Chinese remainder theorem. 4 square roots of 1. So it seems like you have a reasonable shot of landing on like a non-trivial one. And you just have to like check that this is indeed true. Okay, so as a completist, I really wanted to show the proof of this, but then it's a little bit too annoying. So I'll make you do it. Yeah.
I actually don't see why not all A wouldn't have like odd order. Can you dispute that?
Yeah. Well. Okay. So basically, okay, this ZB star by Chinese remainder theorem is equivalent to ZP star cross ZQ star. This is a little math talk, but it's a math major. And P and Q are primes. ZP star and ZQ star are cyclic groups. And they're cyclic groups of order p minus 1 and also q minus 1. And p minus 1 and q minus 1 are even because p and q are primes. So it's like basically your choice, you're picking a random A, you're effectively picking a random number in the direct product of two cyclic groups of even order. So there's going to be at least a half chance that a random element of a cyclic group of even order has even order. And then the overall order of A is like the LCM of the two orders in the two groups. So you have at least a half chance for both of them of picking up an even order. So like you have at least a 3/4 chance actually that like at least one of them is even. Okay, and then there's some like tedium to like check that this part is okay. It's like a couple paragraphs. Yeah, there you go. Just review this lecture when you're doing the homework. And that's the end of the number theory in part 1. So that's the algorithm. Yeah.
In the last lecture, didn't you say that like you can't directly find find L, but you'll find a multiple of L, so you can like get many multiples and like find a GCD to kind of get L, right?
Okay.
But doesn't that have a chance of getting a multiple of L back?
No. So what we're going to do now in the second part of the lecture is it logically precedes this. I'm going to tell you how you can go from that those clues that the quantum algorithm, which does the Fourier transform and everything, give you about L. These clues being like a random multiple of n over L, capital N over L, rounded to the nearest integer, and find L exactly with good probability. And then like that, exact finding of L is taken for granted in like this stuff. Okay. There's one more piece. This also gets like a little tedious if like B is not just the product of two primes. It could be product of some prime powers and more than two. You have to you need one more fact, which I also made you do in the homework in that case, which is that you can recognize if a number is like a perfect cube or a perfect fourth power or a perfect power in polynomial time. Okay. That's, well, I was going to say that's it for number theory, but there's number theory in part 2 as well, but it's like more fun. I like the number theory in part 2. So part 2 is this thing of finding L from the clues. Part 2 of this lecture, I should say. So it's finding L given these clues, which is S. It's like this measurement outcome, which is of the form nearest integer to k times n over L. At least it's of this form with probability at least 40% or something for random k between 0 and L. Okay, so let me just assume that when you get this clue, you're in the 40% chance that it is of this form. And if it's not of this form, then you can just try to proceed with anything anyways, and it may well fail, but if that happens, just repeat everything again. Okay. In fact, as I said, it's also, if this does fail, probably you'll get the second nearest integer to this, and we'll actually see that it'll still work. Okay. And remember, this is like the measurement outcome after you do the Simon style algorithm. You load this into a quantum state, a little n cubic quantum state, do the quantum Fourier transformation, and measure. Okay, so now I'm going to get to this issue that we were discussing about capital N versus capital L. Okay, in order to do this, find L, we're going to use the fact that capital M can be quite large. So, okay, so this is a reminder. L is at most m bits. And we'll choose capital N to be 2 to the little n, where n is, let's say, 10m. Okay? This is going to help us solve this puzzle. And, the cost to us here is efficiency. But it doesn't cost us very much, because this is just 10 times m. In fact, I think everything I'm going to do subsequently, it's conceptually easier if you imagine n is like m to the 10 rather than 10m. So n is quite a lot bigger than m. Okay, that maybe costs you efficiency. You don't really want it to be m to the 10, but it would still be polynomial, so that's fine in theory. it's actually going to be sufficient for it just to be like modestly bigger than m. But psychologically, think of capital N, which is like 2 to the 10 m, is like way, way bigger than L. So it's like a big, this is like the 10th power of this in our current setup. But even if we put m to the 10 here, this would be like exponentially bigger than this. So think of n as really enormous, like hugely enormous, and L is like not that big. I mean, it is actually big because it's like on the order of 2 to the little m, but compared to n, it's going to be tiny. And of course, n is just on power of 2, so capital N over L is definitely not an integer. Well, probably. Okay. But what do we get from this? Well, we get an S which is very close to k times n over L. Can I just invent it for this talk, this lecture, like this notation, exclamation mark. This means like unbelievably close to. Okay? Because how close is it? It's really unbelievably close. It's to like within plus or minus 0.5 over capital N. Okay, and capital N is like really enormous. Okay, so this is unbelievably close. And let me rewrite this. Sorry, this is not. That's wrong. That's like L, but yeah, sorry. This means that S over n, just rewriting here, S over n is unbelievably close to k over L. And this is the thing that I should have said is within plus or minus 0.5 over capital N. Right? Because, S is like the nearest integer to something. So, I mean, you can, add plus or minus 1 to this to make it closer to make this fraction closer to this. Okay. So, the algorithm knows this. In fact, it knows so this is the important thing here. And here, the algorithm knows the numerator and the denominator. It knows the numerator because S is like what it got out of the measurement, and it knows the denominator because it set it up. N is just 2 to the little n, which it knows. So it knows S and N. And its goal in life is to figure out basically this fraction. It really wants to know this denominator. And here's the key claim for the rest of the lecture. From S and N, a classical algorithm can efficiently determine the fraction k over L in lowest terms. That's lowest terms is a term from elementary school. If you have a fraction, right? If k and L have a common factor, you cancel it out. You keep doing that until you get it in lowest terms. And what we're going to show is that once the algorithm gets S and N, it can figure out what this fraction is in lowest terms. And that's almost what it wants. What it really, really wanted was capital L. But we're now, from this, we're like easily done. Actually, there's like 2 ways you can be done in this case. Can anybody think of at least one way? Both of these ways rely on the fact that k is basically a uniformly random integer.
You can repeat this several times, and the LCM of all denominators.
Right. So the only trouble is if like k, the random thing is like co-prime to capital L, so there's no cancellation, then you're set because you just look at the denominator and you're like, that's it. But like the bad thing that could happen is like maybe capital L is even and little k is also even. And so like in lowest terms, they both cancel out. And the denominator of the fraction you figure out is actually maybe capital L over 2. Or maybe capital L is actually divisible by 6 as well. And then your second k is divisible by 3. And so when you take them to lowest terms, you knock off a 3 in the top and the bottom. And so you accidentally get capital L over 3 as your denominator. Well, it was suggested you do this like a few times, take the LCM of the denominators, and you'll get L real quick. So exercise, if you do it a few times, and literally this means a constant number of times in expectation, kind of like in the period finding solution we did when L divided n, and take LCM of denominators, you'll get L with high probability. OK, and that's what you would actually do in real life. In theory land, here's like an even simpler thing you can do, although it's less efficient. You can just hope that k is a prime. No, just a prime number. I mean, yeah, you can, what you really do is just like hope that k is coprime to L. That's what you really want. Has a GCD one with L, but like just be super naive and say like, man, I just hope k is a prime. If k is a prime, then you don't have to worry about anything like it'll be coprime to L. Oh, wait a minute. No, L could be a multiple of k.
But then we'll know k is 1.
Let's see. Yeah, I guess you have to like hope that not only k is a prime, but like L is, that's a little flaw in my reasoning, that like L is not a multiple of that prime. Well, it's also okay. Like L has only about so many different prime factors. So it's very unlikely that k, even if it is prime, will be one of those prime factors. This is just going to be slightly longer than I thought. So what I was going to say, which I guess is a little bit wrong, is this is a little bit rare that you pick a random integer and it's prime. But it's not that rare. The prime number theorem actually implies that if you're picking m digit numbers at random, there's around a 1 over m chance it's prime. And that's actually pretty OK, because if you repeat it about little m times, which is still polynomial, you'll get a prime with high probability. And I thought we were done then, but I guess we're not, because maybe that prime divides L. But L has only log of 2 to the m, like little m prime factors, whereas like the number of primes you're potentially picking from is exponentially large. So the chance that you'll actually hit one of the prime factors of L is negligible. So this will basically work. I mean, this is what you should really do, but like here you have to do like a minor amount of analysis to check it. I thought you didn't have to do any analysis here at all, but to do a teeny bit. OK, so in fact that means that like if you're willing to like take this low but not terribly low chance of succeeding, then you just need one clue. Do you have a question? OK. OK, so let me leave it at that. And so now we just the last thing is to do this key claim. OK. Any questions right now? OK. Good. So now, I mean, forget everything from the rest of the lecture, including up to here, and we're going to focus only on this key claim. OK? Totally new problem. It's like kind of mildly fun as well. So there's a mystery fraction, k over L. And now, without loss of generality, imagine that k over L is already in lowest terms. OK? And you get s over n, where s is set up so that this is like the nearest integer to this, so that s over n is like a really, really, really good approximation of this fraction. Now, capital N is a power of 2 because computers like powers of 2. But we're humans, and we like powers of 10. So let's imagine that capital N is 10 to the n, not 2 to the little n. Okay, this is for expositional purposes. Okay, and so the algorithm in like k over L is a mystery fraction, which is now like in lowest terms. And capital L is the denominator is at most m bits long, and you should in particular think of capital L as much smaller than capital N. And the algorithm gets, well, it's S such that S over N is, as close as possible. It's ridiculously close to the mystery fraction. Oops. Okay. In other words, like, what is that saying? It's like saying that S over N, this is like, when N is a power of 10, it's like 0 decimal S, if you will, right? So this is, it's the fraction k over L to little n decimal places. That's literally it. So k over L is like a mystery fraction, and you're trying to figure it out. And you get it to little n decimal places. And then you're like, which mystery fraction is this? But the important thing is, like, you get it to somehow like many more decimal places than are necessary in some way, right? Like, you get it to tons of decimal places vis-a-vis how large capital L could be. That's the game. So now this imagining is, you don't have to imagine very hard, but like now let's imagine a bit harder. And imagine that L is not just much smaller than capital N, but like maybe it's like smaller than 50. And let's imagine that capital N is 1,000,000. Okay? 10 to the power of 6. Okay? And I just want to like play this game for you. We'll develop a human algorithm for this problem, and then we'll understand how a computer can do it. So let's do the human version of this problem. So say you hit the button, you do your period finding, and S turns out to be 666,667. Can somebody tell me what the fraction k over L is? No? 2 over 3, yeah. Then hey, like you're going to figure out the answer is 2/3. That was easy. How hard can this be? Yep.
But 3 is in the factor of 50, so how would you get an integer over 50 is 2/3?
Oh, I didn't say L equals 50. I said L is bounded by 50. Yep. Okay. Let's keep doing this game. It's fun. So here's another one. Let's put your skills to the test. It's tougher. Say, okay, you're playing again. Still, n is 1,000,000, 10 to the 6, and your promised L is at most 50. Say S is 181,818. Who's good? Who knows what k over L is? So what you know at this point is that k over L is very close to 0.181818. This is the closest 6-digit decimal representation of this fraction. Who knows what k over L is? Yeah?
2/11.
Yeah, it's 2/11. Very good. I'll ask you how you did that later. Well, you already recognize it's 0.090909 times 2. Well, okay, very good. Okay, here's another one for you. We'll just play this all day. Let's say that S is, I'll make it a little easy, 142,857. In other words, k over L is super close to 0.142857. Does anybody know k over L, the fraction? Yeah, it's 1/7. Great, you're good at this. So basically, how hard could it be, right?
This is easy just because it's like we already have this pattern. It's like
Well,
if you pick a fraction like 13 over 43 and write it down.
13 over 43, wow. Who would pick that fraction? Let's say that S is 309,524. Does anybody know that one? Yeah, it's tougher, right? Okay. Maybe it's 13 over 43. Well, you can cheat as I'm going to talk, if you could look it up somehow. Here's actually a way to cheat. But this way of cheating is actually cool because it proves this problem is sort of solvable. You can use a math program. I use it all the time. I use Maple, but whatever, there's Mathematica or Sage or whatever. So I know the commands in Maple. If you go into Maple and you type this, identify 0.309524 semicolon. Oh, you don't have to do the semicolons anymore. It'll give you the answer. Don't spoil it. Very good. OK, good. OK, but now we have to figure out how to really do this, right? OK, how are we going to solve this one? Well, that was a little tricky, so we'll come back to it in a second. Let's go back to solving this one. Well, we already knew how to solve this one, because I guess some people have like a lookup table in their head. They know this fraction. But how could we discover it algorithmically? Let's say we're on this S. So we know that S divided by n is super close to this mystery fraction k over L. You could look at capital N over S, which actually would be a good idea in this case. So you can, of course, efficiently do integer division. And let's just say you do that, integer division, n div s. Maybe this means integer division and also compute the remainder, like you did in 3rd grade, maybe 4th grade. What do you get if you do 1 million divided by s in long division? Well, we kind of know, right? You'll basically get 7. There'll be a tiny remainder, right? You'll get 7. And the remainder will be, I guess the last digit of 7 times this is 9. So the remainder is probably 1. OK, so if you didn't know that this was basically the answer was 1/7, you might have done this operation. Or maybe you might have tried this for whatever reason. And then you would become astonished, because you're dividing by 142,857. So in principle, the remainder can be any number between 0 and 142,856. And it was 1. So something fishy obviously happened, right? I mean, it's fishy. You're like, whoa, this is probably the error. Probably like, this is, had we pretended this was 0, then we would literally know that like n over 7, n over s equals 7. This is basically what we've just discovered is this. N over s is ridiculously close to 7. And therefore, s over n is surely 1/7. OK? Now, that little trick works great if the mystery fraction is of the form 1 over something, which it's not always. But it's not too terrible to go on. Like, what happens if we try this one? Yeah, but how do we know? We don't know in advance that we should look at 2n. Because in general, OK, these numbers are actually at most L. And L is actually 2 to the 500 or something. So there's lots of possibilities for the numerator. But what we're going to do is this. Let's say that S is this one. And I'm going to start calling this S S1 for reasons you'll see. So we'll do what we did last time and hope something good happens. We'll do n integer division S1. And what will the integer quotient be? Yeah, it'll be 5, right? Because I mean, the true answer is 5.5. It's 5. And then, OK, the remainder, it's not easy for you to figure out, so I'll just tell you. It's 90,910. I'll call that S2. But here's the thing. You and I both secretly know, right, that S1 over n is basically 2/11ths. Which means that n over S1 is basically 5.5. So we got the quotient of 5. So that means this is basically 0.5 S1. Right? This is ridiculously close to half of S1, which it is. So now it'll be good if you do this trick on S1 and the new number S2. Right? So now, if the algorithm does S1 integer divide S2, it's going to basically get 2 with like a comically small remainder.
Smells like GCD.
Smells like GCD. Very good. That's exactly what we're going to do. Exactly. So this is this number, integer divide this number. It's actually, OK, doesn't work out super great. It's 1 remainder 90,908. Which doesn't look that great. But you can also, it's not hard for an algorithm to notice that this is the same as 2 remainder -2. OK? And this is a preposterously small number. Let's say if you always, instead of doing your remainders between 0 and 90,909, you do them between -45,000 and +45,000. Then you're like, holy cow, it could have been anything between -45,000 and +45,000, and it was -2. Like, I think something fishy has happened. OK? And so now you're kind of done, right? Like, what do you conclude? Once this like miracle has happened. That's a shame. So now you surely know, okay, that like S1 was basically 2 times S2. Okay? And then you look back and you say, oh, well, N, that was basically 5 times S1 plus S2. Right? You had 5 S1s, and you had this remainder, and that remainder turned out to be twice S2. So then you plug this into this, and you get, that's like 10, 11 S2. OK? So your original S is 2 times this S2, and N is 11 times this S2. So therefore, S1 over N is super close to 2 11ths. OK, so as was suggested, what I'm getting at here is, given N and S, you basically just start doing the GCD algorithm, like Euclid's GCD algorithm for N and S. And at some point, you'll get like a number that's like shockingly and suspiciously close to 0. And then you're like, OK, I see what's going on here. And you figure out K over L. So let's do it in that one case that was a little bit harder up there. So the algorithm is basically do Euclid's algorithm for N and S, should maybe convenient to call S1, till you get a preposterously small number, which, OK, we'll quantify at some point. OK, so let's do it with this S, actually. And N was 1,000,000. OK, now I'll actually do Euclid's algorithm here. OK, so OK, in Euclid's algorithm, we do the integer division, like N divided by S is 3, and the remainder is 71,428, which maybe I'll call S2. And then you do S1 div S2. So that's 300 and whatever thousand divided by 71 or whatever thousand. It's 4. Remainder 23,812. We'll call that S3. We do S2 div S3. That's 2. Remainder 23,804. Again, the suspicious thing has actually happened, right? If we do our remainders between minus half of this and plus half this, we would say this is 3. Remainder -8, okay, which is comically small. And now we'll do this little trick here. So the final thing was that we saw that S2 was basically 3 times S3. And now we look back up here and we see, oh, S1 is basically, well, actually is 4 times S2 plus S3, which is basically 13 S3. We do it all in terms of S3. And then N. Well, the thing that we finally got is that this S3, it was a weird number, but like S2 was basically 3 times it. And then from that, like S1 and Sn can be written as like small integer multiples of S3. So N is 3 times S1 plus S2. That's sort of the first step. But now we can write both of these in terms of S3. So it's like 39 S3s plus 3 S3s, which is 42. Look at that. 42 S3. OK, and so the final answer, S1 over capital N, is 13 over 42. That's the great answer to the question. You said 13 over 43, which is incredible. Yeah. So you're very close. But actually, the point is, 13 over 43 is actually going to be considered not that close. Even though they seem close, that's the reason, in fact, why we take capital N to be quite large compared to L. So that 13 over 42 will actually be kind of far from 13 over 43. And even though they seem close, you'll notice the difference if you take it out to enough decimal places. And the point is to take capital N so it's enough decimal places. Yeah, so it turns out this is 0.309523895. OK. So on one hand, I wanted to say, well, we're basically done, right? Like that's the proof. But well, OK, that's the algorithm. We should do the analysis, or at least sketch the analysis. So let's do that. Instead of with a million and whatever, we have to do it with generic L and capital N and everything. But in order to recap this analysis, as was noted here, right? What's basically going on here is we're doing, even though the algorithm doesn't know this, when we do GCD of N and S, when S is like incredibly close to 1340 over 42 times N, then what does Euclid's algorithm look like? You got N, and then your next number is basically 1340 seconds times N. OK. And then in Euclid's algorithm, you divide this by this. The quotient is going to be like 3. And then that's so this times this is 39 over 42. So what's left is 340 seconds. So we get about 3 over 42 n's. OK, and then in Euclid's algorithm, you do this divided by this. The quotient is about 4. Well, it's 4, actually. And what's the remainder? Well, 4 times this is 12 40 seconds. So there's 1 40-second left over. OK, and by the way, the algorithm doesn't know, like, these are the fractions. But I'm just retroactively like seeing what happened, given that we know the fraction 13 over 42. OK, so then it does this divided by this. There, the quotient is 3. And the remainder is basically 0. OK, and that's when it stops. So that is just what happened here, but written a bit more clearly. And I just want you to compare this to and notice that these are basically the exact same steps that you would get had you done GCD of 42 and 13. OK, again, the algorithm doesn't know this, but this is good for analysis purposes. Compare this versus what you get if you do this. Right? OK, this one did a long time ago. You got 14, and then 42, 13. Quotient's 3, 39. Remainder is 3. Quotient's 4. Remainder is 1. 0. That's it.
I think it's easier to think if you just imagine that n is just like equal to 42 times some t, and s is equal to 13 times t.
Yeah.
Then you have exactly the same thing, right? It's just like, yeah. It's not easy to think in terms of quotients.
Yeah. Well, I mean, that t is the thing that we call k. I'm just thinking this is like some integer. Yeah.
No, it's not k.
isn't
It's
it?
something that you need to multiply k over L to get n over s. That number.
Maybe. Yeah.
Right? Like n over s is kind of equal to k over L, right? But then k over L.
L over K.
L over k, right? But then L over k is kind of like much smaller fraction.
Yeah.
So now you want to multiply the numerator and denominator by some number to get n over s. So you can just think
Yeah.
that n and s are just like 42 times some number and like 13 times some number.
They're close to being that,
Yeah,
yeah.
close, like close, yeah.
Yeah. Yeah.
And then you get exactly the same numbers.
Yeah, so I wrote this down to say that, like, if the mystery number happens to be fraction, happens to be 13 over 42, and you do this algorithm, you do it kind of like blindly, not knowing these fractions, but until you like notice that you hit 0, then the broad steps will be as if you had done GCD of, L and K. And we know how to analyze the GCD algorithm. So, so the broad steps are like basically these things, are as in when you do the GCD of L and K. And these are m-bit numbers. And you analyze, the GCD algorithm, Euclid's algorithm on m-bit numbers. Basically, every couple of steps the numbers have, you lose a bit. So basically, means there's like at most, 2 m or so broad steps. And at a high level, what that means is this is actually, there's error here. But the error is on the order of plus or minus 1 over capital N. And that's really tiny. And since I only have 3 minutes left, I was going to do the full analysis, but I won't. It'll be in the notes. But let me give you what I hope is like a super convincing quick analysis, which is that actually as if you keep track of what literally happens here, this is wrong up to plus or minus 1 over capital N. And actually, this is even wronger because the error gains a factor of 3, if you think about it. And going from here to here, the error gains a factor of 4. And so the errors kind of accumulate. The extent to which this is correct, gets worse and worse. But even if you're super naive, and you can be smarter than this, certainly at worst, the error goes up by a factor of capital L at each step. And so if you do it, capital L, multiply L times L, m times, but against 1 over capital N, you could still make this very small. I mean, this is at most 2 to the, capital L is at most 2 to the little m, so this is at most 2 to the little m squared. So actually, if you take capital N to be 2 to, a lot bigger than 2 to the m squared, which means n a lot bigger than m squared, then I hope you're convinced that things would be really fine. And you actually don't mind taking n to be a lot bigger than little m squared. Now, I actually told you it's suffice to take n to be 10 times m. And I won't get into it in 1 minute, but if you take a little bit of care, you can just look at the notes. The errors don't accumulate as bad as this. And in fact, if you keep careful track of the error here is actually just 1 times, 1 L times the original error. So the final error is sort of actually more like L over capital N. Okay, and so then maybe at some point you get an L squared. It's basically enough for capital N to the little n to have little n bigger than little m by a constant factor. But OK, I will not get into the details, but I think you should probably find this convincing that by taking little n suitably large compared to little m, these errors will really be negligible, and you'll really nail things down. And you'll somehow never get confused between if you think the answer is k over capital L, and the true answer is k prime over L prime. What is the difference between these two things? If you put them to a common denominator, the difference is at least 1 over L times L prime, which is 1 over at least 1 over 2 to the 2m. So again, like, you know, if little n is way bigger than 2m, these errors that are on the order of 1 over capital N are way smaller than this. So this really kind of tells you that, you know, you just need slightly more than 2m digits of a number to tell the difference between any two fractions where the denominator is at most m bits. Okay, so I hand waved a little at the end, but hopefully it's believable. And that's it. That's Shor's factoring algorithm. OK, so I'll see you on Thursday. Also,